1976 to 1979. From 1991 to 1993, he served as Director of Energy Research at the Department of Energy. He's a specialist in modern optics, optical and radio frequency spectroscopy of atoms and molecules, radiation propagation in the atmosphere, and spin-polarized atoms and nuclei. He's published over 200 peer-reviewed scientific papers. He's a fellow of the American Physical Society, the American Association for the Advancement of Science, and a member of the American Academy of Arts and Sciences, the National Academy of Sciences, and the American Philosophical Society. He was awarded an Alfred P. Sloan Fellowship in 1966, an Alexander von Humboldt Award in 1976, the 1997 Broida Prize, and the 1999 Davidson Germer Prize of the American Physical Society, and the Thomas Alva Edison Patent Award in 2000. He is an entrepreneur. He was co-founder in 1994 of Magnetic Imaging Technologies Incorporated, a small company specializing in the use of laser polarized noble gases for magnetic resonance imaging. The astronomers in the room will know him as the inventor of the sodium laser guide star, which was a federal project to project guide stars for adaptive optics into the upper atmosphere, exciting the sodium layer. If you were here last year for Claire Max's talk, she talked about the declassification of that project and its use in astronomy to deblur the atmosphere. Today he will be speaking on why has there been no global warming in the past decade. So please welcome Dr. Will Happer.
Well, thank you for that nice introduction, Dr. Seminar. Appreciate it. Let me see if I can get this stuff to turn on. Okay, well, I can start. Okay. So this is the title of the talk. Is this working okay? Is there a laser pointer here by any chance? Big one. Pointer, this kind of pointer is fine. Okay. All right, so let's talk about global warming. And people often ask me, why I think I'm qualified to talk about global warming. And actually, I was the author of one of the first books on global warming in 1982. Some of the parts being radiation transfer. And so I've maintained an interest since then. Of course, when I was at the Department of Energy, I funded most of the DOE work on the environment and global warming. So I've kept an eye on it for a very long time. And so what the fuss is about is the fact that there's no question that CO2 levels at red curve are steadily going upward with time. It's 1960, it's 2010. This is largely due to Charles Keeling, real hero for getting these measurements going. But you measure CO2, and sure enough, it's increasing. It's about half the amount of increase that you would expect if all the fossil fuel CO2 went into the air. So half of the CO2 is going somewhere else, perhaps the ocean, probably the oceans. Some of it perhaps to the land also. And the temperature is plotted in blue here. So the temperature was decreasing slightly until about 1975. This is when there were articles in Newsweek and Time about the coming ice age, and they quickly changed their spin for the next 20 years when it increased to about the year 2000. It hasn't changed much since the year 2000. We're now 2014. And I think most people admit that. So this is the surface temperature of the Earth. reasonable to ask why that is and how well did we do. Well, here's how well I did with my colleagues in 1982. We predicted a warming per decade of about 0.2 degrees per decade, so this was our prediction. Right in the middle, in fact, maybe slightly on the high side of everybody else, all the other computer models. The red is what's observed. Okay, so this is over a time period, this is from Nature, like last year, fall. So this was 1998 to 12, pretty bad. If you go back to 1993 to 12, it doesn't get any better. And so all of the computer models are predicting too much warming. So the climate is so complicated, nobody really knows. There have been dozens of proposed explanations for this puzzle. No one has converged on an explanation that everyone agrees to, but the press is beginning to notice. This is from the journal Der Spiegel, and shows these black dots measured warming. This was up to about 1913, I believe, or 12. This has continued to be flat. So the colored bars are the various computer model predictions, all of them going up much faster than the actual observations, which aren't doing anything. That temperatures, observed temperatures, completely stable. There are fluctuations. We'll talk about a few of them. For example, this comes from averaging surface data. That's always, you're worried about your sampling error. So you can also look at spatial measurements. And so this is measurements from satellites. And what you do here is you look at the 60 gigahertz radiation coming up from the atmosphere, which is in the middle of an oxygen line. And you simply do radiometry on it. See, this is due to thermal radiation of the oxygen. And with an onboard calibrated black body, you compare the radiation of the atmosphere to the radiation of the black body at different frequencies. So you can look down close to the surface, or up high, near the top of the tropopause. This is as low as you can really get the lower atmosphere, the lower troposphere. And there's a big spike here in 1998. This was the big 1998 El Nino. It was one of the largest we've had in my memory. There's a more normal one here in 2011. There may be one coming now. We should all hope so, because it will bring rain to California, which we desperately need. But there's no trend. El Niños are, you'll hear a lot about El Niños, and the normal condition in the Pacific Ocean is that you've got trade winds blowing from the Americas toward Australia and Indonesia, and of course from Africa to Americas. That's what drove the slave trade, sorry to say. But these easterly winds push the warm surface water toward Indonesia. So normally there's a pool of very warm water off of Indonesia and Australia. The thermal climate is very heat, a lot of warm water, heat there. But for puzzling reasons, every 4 or 5 years, the wind stops blowing, and then there's nothing to keep the water, up against Australia, so it spreads out over the entire Pacific. So the whole ocean, the whole Earth looks like it's warmer, because this warmth that was normally hidden beneath the surface of the ocean is suddenly opened up over the Pacific. Every now and then you get the opposite extreme, where the wind's really strong, and then you push everything to the rest of the Pacific. So not La Nina, normal, El Nino. That's been with us for many, many centuries. You can tell because the Padres in South America kept a good record of the fish catch off of Peru and Ecuador. And you notice under normal conditions, because of this blowing wind, there's lots of rich, fertile water coming up, so there's very rich fishing from the bloom, fertilized water off the coast of South America. But when the El Nino comes, it stops rising, and so all of a sudden there are no more fish. And so you have a year where the monastery coffers are quite great there. And you can look at those records. They're many, many centuries old. There's no sign of any change over those many centuries. They come and they go. people always question my credentials at all, but they never question how it works. So this is how it works. And they're right. I mean, I'm simply a physics professor, practicing physicist, and he's a Nobel laureate, for climate. And so this is the cover of his most recent book, Our Choice, and this is the Earth. And as he says, it's been slightly retouched. So let me show you the original for this picture. So this is the original that was retouched. You can tell that he doesn't come to this, but I looked it up and I found it. And the big difference in the retouching is most of the clouds have been removed. So this is the original, and this is our beautiful Earth. It really is beautiful. I mean, the blue oceans, the lovely clouds, and the green forest. We should all be environmentalists. I consider myself a strong environmentalist. I'm all for it. And so the cover has removed the clouds. And, well, that's okay. It's a minor change, but he goes on because this is a cover that you can open it up and swing it back so you can see the inside cover and see what Al's the view of the future. And so it's the same thing, but it's to warn you what will happen if you don't listen to Senator Gore. And here's a hurricane about to hit North Carolina, and what's particularly alarming is it's rotating the wrong way. So I'm becoming afraid on haywire as a result of not listening to your betters. Here's a hurricane rotating the right way and about the right place. Here's another really worrisome thing, a hurricane right off of Ecuador. You can see it's right in the middle of the tropical convergence zone, right on the equator. No one has ever seen a hurricane there. Let me show you where hurricanes form. So here's where Al had a hurricane. And of course, on the equator, there isn't any Coriolis force. So, if you're a hurricane, you rotate the same way the Earth is rotating. So in the north, you rotate around like the Earth is going. So you seem to be going like a right-hand rotation. And if you're in the south, looking down on the Earth, it's more like a left-hand rotation. Right? If you're at the equator, you can't figure out am I north or south, so you don't form at all. You'd like to be a hurricane, but you can't because you don't know how to rotate it. Well, and this whole field is full of stuff like this. That if you really push on the science, it isn't there. It sort of looks plausible when you look at it, and then when you push on it, it's a house of cards. Okay, well, you need to know a little bit about. In fact, you need to know a lot about the atmosphere, but here's some of the basics that you really need to know, and that is that we live in the troposphere. This is the region of the atmosphere where most of the heat transfer is by mass motion, warm air going up, cold air falling down. There's not a whole lot of radiation transfer at the surface. You start being dominated by radiation transfer where CO2 can make a difference. And when you get to the top of the troposphere and into the stratosphere, where this churning motion of the atmosphere is stopped, and where the temperature drop is stopped. So if you ride a jet plane to California, or you're typically flying just above the tropopause where this churning is below you, so you don't get a rough ride. And also you get the fuel mileage there. The plane is designed to fly there. But in this region below, it becomes extremely cold. It's typically about 200 Kelvin, 210 Kelvin at the tropopause. And this is somewhat latitude dependent. The tropopause is very high over the equator, so there's lots of sunlight to drive up this convective motion, and it's quite low over the poles. Okay, so that's something to keep in the back of your mind always. And of course, there's a lot of structure to that turbulence. There are these sort of large-scale cells that they don't look nearly as regular as this. If you actually look at a satellite picture today, you can recognize them, but they're all sinuous and distorted. But roughly speaking, most of the sunlight is in on the equator, so it's driving huge convection towers at the equator, bringing up moist air, which loses its latent heat, and down comes rain. And so by the time you get to the top of the tropopause at the equator, you've got extremely cold and extremely dry air. So paradoxically, if you look in the infrared, the Earth was coldest at the equator. That's because these cells have driven up the air so high, it's cooled off so much. And then part of the air goes north, part of it goes south. It's highly dehumidified. It's very, very cold air, and it comes crashing down at about 30 degrees north, 30 degrees south. These are the latitudes of the big deserts of the Earth. So the Sahara Desert is over here in Africa, where there's this descending branch of very, very cold, dehumidified air. And the Atacama Desert down in South America is the same with parts of the Australian Desert like this. All right, so there's rough, large-scale structure as well. And the last thing to remember is that the reason we can live on Earth is because of the warmth of the sun. If we didn't have sunlight, then, for example, the Earth or like Pluto or even beyond Pluto, where there's no radiation at all, we can calculate what the Earth's temperature would be because there's a certain amount of heat still being formed from the residual gravitational compression and radioactivity in the core, potassium, uranium, thorium, and it would be in below 200 Kelvin. You could see it in the far infrared. People are designing satellites for NASA to look to see if there's anything out there, but so far we don't know. But anyway, you wouldn't want to live on a planet like that. You need sunlight. So if the sunlight warms us, some of this warmth has to go back to space, otherwise we would ache. And so from the surface itself, it's heated by the sun. Part of it, the way up to the troposphere, you're being carried by convection mostly. Reaching the tropopause and above, the radiation is sent back into space entirely as far infrared radiation. So looked at from space, the Earth, if you're not looking invisible, if you're like a rattlesnake who can see far infrared, you would see this glowing body, this glowing sphere that's emitting thermal radiation. The warming by the sun is actually helped a little bit by greenhouse gases because it's quite difficult for the surface to radiate into space directly. That's because here are the black body curves of the Earth at various temperatures, very cold, like at the poles, very hot at the equator. So the hot one is the purple one, and the cold one is the black one. And you can see there's only a narrow window where it's possible for a photon that leaves the surface to get all the way to space without much chance of being absorbed. So this is the absorption. So there's an infrared window here where you can get out to space. But over most of the black body curve of the Earth, you've got to get out by multiple scattering as an infrared photon, and of course by convection. And what is causing this is predominantly water vapor. And this is for clear, no clouds. If there are clouds, all bets are off. Carbon dioxide is sitting at the edge of the water vapor band. So carbon dioxide is a contributor. And then there are lesser contributors, ozone, methane, nitrous oxide. And of course, radio scattering really dominates in the blue part of the spectrum, but that is not where the Earth radiates anyway, so it affects the sunlight coming in, but not the radiation going out. So this is the overall picture of the radiation balance. Greenhouse gases are mostly water vapor. They're very important, and without them, the Earth would be too cold to live on. So we're happy to have the greenhouse effect. These are actual photographs of the Earth. It's important that every chance you get, you should really look at data. You shouldn't look at computer models and displays. You should look at actual data. And so this is data of the emission of the Earth at the Sahara Desert. And so this is increasing radiation going up. This is wave number going this way. So this is the energy of the photon, traditionally measured in waves per centimeter. you can see a lot of radiation in the infrared window. This is the window. There's some attenuation here from ozone. Here's CO2. CO2 is completely optically thick, but you see there's still a lot of radiation to space, even in the CO2 band. That's because this is radiation from the stratosphere, and the spike in the center is a high stratosphere. So one way to tell whether they're kidding you about some spectrum usage, this spike isn't there. You know, it's somebody's computer model. Look outside. It's a very high stratosphere, and if you're looking at the reverse, if you're looking up, the spike is there, but it's negative. And there, that's very interesting. It's because you're freezing to death in the observatory, and so it's the CO2 in the air in your laboratory. The center of the CO2 band is so intense that just a few meters of radiation is enough to produce. A few meters of air is enough to produce that spike. Okay, so look for the spike in your electrically heat. But this is interesting. Let's talk about it a little bit more before we move on. The most interesting of these four graphs, I think, is the one of Antarctica. So this is looking down from satellite, must be sun-synchronous, over Antarctica. And there you see CO2 is actually in emission here, so it is the strongest part of the spectrum. So it's cooling as fast as it can, actually cooling the troposphere and the low stratosphere of Antarctica. And the ice sheet itself is exceptionally cold, 180 degrees there. And there's essentially no water. You can just barely see a little bit of water on that side, a trace of water over here. The ozone is still there. But almost anywhere else on Earth, except for Antarctica, you always see this strong CO2 band. You always see, well, you don't always see water. You see a lot of water, for example, with the Sahara. But you don't see very much water over southern Iraq because that's in this descending branch of the Happer cell. And so the air over Iraq has been dehumidified and has very little water in it, so there's just a trace left there. But CO2 everywhere. And CO2 always radiates. It's typical radiation at the minimum here is about 220 degrees Kelvin, which it turns out the temperature of the lower stratosphere. All right, this has been introduction, and now we're going to get down to bare metal physics. Okay, so now my wife is welcome to leave now. But she can say that's even better. So this is a one slide summary of global warming. So I hesitate to put equations in the talk, but I will briefly here. So this is the warming temperature from added CO2. So what the added CO2 is, it causes what they call radiative forcing. So that's delta Q2. So that's the radiative forcing from doubling CO2. You take a present amount and you double it. Turns out it doesn't matter whether you double it. It goes logarithmically. So if you double it again, you just get the same number. You don't get 4. You just get another factor of delta Q2. And we'll talk about why that's so. And so naturally you would expect the warming to be proportional to the forcing power. And you take the ratio of that power to the natural radiation coming out of the Earth. So this is the mean radiation of the Earth to space, so P in the denominator. So that's a dimensionless number. Cubes have the same dimension. There's a single factor of temperature, so this is dimensionally correct. And then it's got some correction factors. This 4 comes from the Stefan-Boltzmann law, T to the 4th. There's a feedback factor here. It's very important. 1 minus a feedback dimensionless feedback. And so lots and lots of physics is hidden in all of these parameters, especially the feedback parameter, but also part of the radiative forcing. So whatever is causing the non-warming for the last 10 years, it's in either that factor there in the numerator or this factor F in the denominator, either feedback or forcing. Most people, if you talk to people whose lives depend on it, would probably bet it's in the forcing. But I'm going to tell you about other problems in the feedback, but I'm going to tell you about problems in the forcing too. Okay, so that's a seed to put in, to put in your bonnet to think about. All right, so here's this pollutant. I keep hearing it called pollutant body. I want to put the parenthesis on down, carbon pollution. Here's the color. And the CO2 molecule is a linear molecule, carbon in the center, 2 oxygens on the outside. And this has 3 vibrational modes. And the highest frequency mode, the carbon moves, say, to the right, the 2 oxygens move to the left. It remains linear, and that's quite a high frequency. So high, in fact, that it doesn't interact with thermal radiation. So it's interesting. It's often used for, I have a little CO2 meter that uses this particular mode here, but it doesn't seem to be working, so I won't use it for this talk. But the real villain in all of this is this bending mode here. So the CO2 is this linear model, you can bend up and down like that, right? And this has a central frequency, I like to call it Satan's numbers, right? 666, the mark of the beast, right? So it's waves per centimeter. It's actually 667, but it's it doesn't make it to the. And then there's a symmetric stretch here, and that doesn't have any dipole moment changes, so that actually has no direct effect on global warming, but it does affect these other modes because it mixes with them. If you look closely here, if you double this frequency, it's practically the same symmetric stretch frequency. So this mode easily interacts, the harmonics of this mode easily interact with both this symmetric stretch mode and symmetric stretch mode. That greatly complicates the spectrum of CO2. One of the reasons that it's such an interesting spectrum. And the guy who first really pointed that out and explained why it was so complicated was Enrico Fermi. Fermi is one of my heroes, and not least of which is because he occasionally made mistakes. Look at the fine structure constant, h bar squared over EC. I don't know how many people fine structure means anything to me, but it's really supposed to be E squared over E bar C. So we got it upside down, but it doesn't matter. At least not for Jeremy. Okay, so anyway, these are the various modes of this molecule. Now, the CO2 molecule has angular momentum around this axis, right? So as it's vibrating back and forth, you can turn around this axis. So this is the angular momentum around the long axis. And of course, it has vibrational energy. The faster it vibrates, the more energy. So these are the different energy levels of CO2. The notation here is from the HITRAN database that's assembled by Air Force Cambridge. It's a very, very nice database. And what I've drawn here is the centers of the vibrational transitions if the molecule were not rotating. But of course, the CO2 molecule is tumbling like a baton, like a bandmaster's baton. And that spreads all of these absorption frequencies all over the place. And here you can see these Fermi resonances. That's what puzzled the first people who started looking into this. These states shouldn't be there, right? And it's because of the admixture of the bending mode with the symmetric stretch mode that you can see these states. Okay, well, this I hope there are a few students because I have $10 for the winner who will tell me. You have to be a student. Yeah, it's not fair if you're a PhD. You're not smart enough. Okay, I'll count down. 10, 9, 8, 7, 6, 5, over $10. 3, 2, okay.
I guess you have a transition from j equals 3 to j equals 3.
That's okay, but you're close. Try again. I'd like someone to win. That's close, very close actually. You're thinking in the right direction. I got this off the internet, so just to remind you, when you look at something from the internet, it's pretty official, but it's often, flawed. Okay, well, yeah, that's, you win, you're here, here's what's wrong, it's this transition, 0, 0. No one has ever seen a 0, 0 transition, in physics, and that's because photon has spin 1, right? So if you emit or absorb a photon, you have to change the state by at least 1, just to accommodate the spin. And of course, you can be quite a bit more than 1 if you have orbital angular momentum, which you see all the time in nuclear physics. But anyway, you're focusing on the right thing. It's the selection rules for rotational transition. So this represents the rotation of this molecule. By the way, I have a model of the bending mode here. This is actually a shower bar. But my wife let me cut it out, but it sounds great. And so this has a bending mode. So that's the bending mode of this. You can actually hear it beating if you listen closely. A little bit of modulation, and all the CO2 modes beat also. They're all double because of this rotation around the axis. And it's also very, very small. You can just barely measure it with a spectrometer. Well, anybody with perfect pitch? What frequency is it? Okay, well, I'm not a musician to know what that is, but you can measure this on the internet, which I did, and it's 554 hertz. So it's actually pretty close to 666, isn't it? If I would cut that down a little bit, it would be a better representation. Oops, damn it. We'll have to pause here. I should never. Okay. All well. Okay, more numbers. Now, these modes of the CO2, both the vibration and the rotation, the number that actually contribute to global warming is enormous. It's typically 4,000. So there's huge, huge numbers that are involved. And so to characterize these modes, the key number is the attenuation coefficient. So this is the E foldings per centimeter of air. And that's written as the number density, and that's what's increasing over time of the burning of fossil fuels, perhaps other reasons too. And the cross-section for the transition from the excited state to ground state. I should probably call them lower or upper because there are many excited and ground states. And the cross-section is typically written as an oscillator strength and a line-shape factor. Line-shape factor is something that's an area of 1. It's a function of frequency. Oscillator strength doesn't depend on frequency, and here it is. And it's a little different than we would normally encounter in atomic physics or in, other areas of physics, because in molecular physics, there's almost always some thermal population of the excited states. That's not true for nuclear physics or most of atomic physics. So you not only have to have absorption by the atoms in the lower state, but you have to have stimulated emission by the atoms in the upper state. So these line strengths are sort of like oscillator strengths, except they're temperature dependent to take into account simulated emission. And it's very, very basic physics. Here's the partition function for the molecule, which goes into this. So this basically tells you how many molecules are in the lower state, how many molecules are in the upper state with this Boltzmann factor. Now, what I'm going to focus on for the rest of the talk, and I certainly don't claim this is the reason for non-warming, but it's certainly one of the suspect reasons. It's not the oscillator strength. These are measured. There's no way you could possibly calculate these precisely. So they've been very carefully measured by very, very good people. I think they're fine. There's nothing wrong with them. But the line streaks are not very well known. And that seems surprising. So let's talk about line shape factors? Well, the simplest line shape factor, in fact, many computer models use this line shape factor, is a Lorentzian line shape. So this says if you're asking how does the absorption depend on the frequency of the radiation, well, it goes like the detuning of the frequency that's being emitted from the resonant frequency of the transition, vibration, rotation, transition, and then it has a factor that measures collision, broadening, natural broadening, etc. In the case of CO2, it's essentially all collision broadening, and that's an important point to keep in mind. The natural width is completely trivial. So broadening parameter, central frequency, and these are measured. So if you go to the Air Force HITRAN database, you can find these numbers there. Again, measured very carefully, but they only work if you assume the line has a shape. So it's one of these sort of topologies. You assume it has a shape, you pick the parameter, it fits. Okay. Well, at the very highest parts of the atmosphere, 40, 50 kilometers, there are so few collisions because the pressure is so low that the line shape tends to be dominated not by collisions but by the Doppler motion of the atom. Some are moving toward you, some are moving away, molecules I should say. And so you have to take a convolution of the Lorentzian line shape with various velocities of the moving atom. So that's called the Voigt line shape. So, Voigt line shapes are almost universally used in models, with some corrections. Some good people actually do some of the corrections. I mentioned CO2 is characterized by this huge number of line streams. So here they are. And to add to the complication, there isn't just one CO2 molecule, but there are various isotopomers, right? So the most abundant is oxygen 16, carbon 12, oxygen 16. But there's about 1% carbon 13, and so that's these blue things here. They fill in some of the gaps. They make a different carbon 13 does. And then there's the different oxygen isotopes. Oxygen 18 is not that rare. Even oxygen 70 is considerably rare. So this is a very complicated molecule. And the reason it's got this huge spread is because of the Fermi resonance that we talked about. So it's because of this accidental degeneracy and twice the frequency of the bending mode and the fundamental of the symmetric stretch mode. Okay. Now you can take these oscillator strings, since they have the dipole matrix element, and quite easily calculate the radiating decay rates of CO2. I know when I first looked at this, I was surprised that they're so slow, but the typical number, it's a rare transition in cesium where the decay is as fast as 1%. So the radiative lifetimes are typically many seconds. And that means so if all the CO2 molecule can do to get rid of its energy is radiate, it has to have a long, long time without any collision radiate. And so these are from, the points are all from measurements. They're very good measurements. I'd be surprised if they're more than 5% error in any of them. And you notice they all slant a little bit upward to the right. So this is frequency going this way, and in fact, they're scaling very nearly as the fourth power of the frequency. And those of you who work with lasers, you're a little puzzled that the fourth power. It really should be the third power, right? Because the spontaneous decay rates go as the frequency cubed times where the dipole matrix element. But this seems to me that there's a slight systematic shift of the magnitude of the dipole moment itself as you go to higher rotation states. Okay, now let's see what this does for radiation transfer. And the first thing to notice is that there's a huge effect of atmospheric pressure. So the red curve is the cross section for absorption near the center of the CO2 band. Near the center of the CO2 band at the surface. Okay, so 1 atmosphere pressure, and it's very structureless. You can practically see nothing. If you go to the tropopause, 11 kilometers, you can just barely begin to see that there's some line structure in there. And to really start seeing the line structure, you have to go up to nearly 50 kilometers where you begin to see that this is a sequence of individual rotational lines, few branch lines, except for 0, 0 that we talked about a minute ago. When one is doing radiation transfer calculations, you have to really take this into account. If you don't take this into account, you won't get an answer that you can be confident of. So how do you take this into account? A lot of this actually goes back to astronomy. And so the real hero for radiation transfer was Carl Schwarzschild and Milne, who took Schwarzschild's work and made the Schwarzschild-Milne transfer equation, radiation transfer equation. So this says, for example, you can look at other altitudes, but for simplicity, look at the radiation coming down to the Earth from above us, from the CO2 above us. It turns out that it's a sum of contribution from all possible altitudes. So Z is how high above us the CO2 molecules are. K is the attenuation coefficient at that altitude, which is very strongly altitude dependent, both because of the pressure brought in and also because the pressure is dropping rapidly, so there are less CO2 molecules. And then this is attenuated by the optical depth, so it can't get to us directly unless it's reasonably close to the surface. And the coefficient here is the famous Planck brightness that was invented by Planck and which really ushered in quantum mechanics and physics. So that's where it came from this formula. And so these are the guys involved in radiation transfer. All right, so you take that equation I showed you. Here's the Schwarzschild-Milne integral equation. You can integrate it. That's not hard to do with modern computers. This is what you get. So what you're looking at here now is the downwelling radiation per unit of frequency in the middle of the CO2 band, assuming nothing else, no water here, no ozone, just atmosphere and CO2. And so the green band is less than 1 part per million. Okay, so if you have less than 1.4 part per million, you calculate this much downwelling, still quite a bit. If you're at 400 parts per million and use the Schwarzschild-Milne equation, you get this red line. And if you say, well, how can I get the same area and fit this with a rectangle? If you get the blue line, actually it doesn't fit too badly. And that's not by accident. I'll explain why that works. And this square fit is important because it's connected with the logarithmic response of warming to additional CO2. And what I mean by that is this integral that we talked about, let me remind you again what the integral was up here. So that what I was plotting on that, the color is this number J, the downwelling at 0 altitude, surface of the Earth. And so if you now take a step further and calculate versus the CO2 concentration, what is the downwelling in which you put the CO2 concentration on a log scale? This is a beautiful straight line. So what this is telling you is that the downwelling flux is not proportional to the CO2 concentration until you get well under 1 part per million. So in the region we're in now and have been in forever, the flux is proportional to the log of CO2 concentration. So that means if we double CO2 and we add a little bit of downwelling flux, if we want to double it again, we have to have 4 times as much CO2 than we have now. So let me show you in pictures what that is. The first person to notice this was actually Arrhenius, Conti Arrhenius, and he was the first really serious scientist to look at global warming from CO2 back in 1890 or thereabouts. And here is a quote from his book, which was around 1900. I'm sorry, I don't have the exact time, but he says if the quantity of carbon dioxide in the air should sink to 1/2 its present percentage, the temperature would fall by 4 Kelvin. Diminution by 1/4 would reduce temperature by 8 Kelvin. On the other hand, doubling would increase it by 4 Kelvin. Increase fourfold, you get 8 Kelvin. So this is this logarithmic behavior. The formula for what Arrhenius first said, and he understood it perfectly well, is that the warming or the forcing, you see the warming proportion to the forcing, goes along with the concentration on the Arrhenius. And look what that does. That says that if we agree, and by the way, Arrhenius' figure is 4 degrees per doubling, and IPCC is 3 degrees per doubling. So, since Arrhenius' time, all IPCC has managed to do is decrease the number by 30%. And if you look at what Arrhenius had at his disposal in his data, it was a shambles, so it's amazing that they're as close as they are. For example, there were no satellites, there were not even good spectrometers, so he had estimated the attenuation of CO2 in the Earth's atmosphere by looking at attenuation of infrared from the moon, of all things. So, again, he's sort of a hero for what he was able to do for nothing, but look what that means. That means that here we are at 400 now. It almost doesn't matter if you double it, compared to what we've already gotten from the CO2 that's already there. So here we are now. If you assume that the doubling sensitivity for warming is 2 degrees, well, let's see, IPCC, this is the official number, 3 degrees. So here we are now at 25, I'd say 30 degrees. If we double it, we get over here to 28 degrees. And to get another 3 degrees, you would have to quadruple it, so we're way off scale here. But nobody knows what the sensitivity is, so they're pretty sure it's logarithmic. I'm willing to bet it's logarithmic, but what the coefficient of the logarithm is up for grabs. And that's because there's so many complications and clouds and water vapor, all of that has to be folded in a believable way. And it's pretty clear from what nature is telling us that we haven't got it right yet. Okay, but why is it logarithmic? The reason it's logarithmic is if you plot the cross-section, I explained how you get the cross-section, on a semi-log scale, they're remarkably like a triangle. And I should have a reference here. This is something noticed by people at the University of Arkansas, and I can give you a reference if I should have had it written down, but I put it there. But okay, so that basically tells you that the cross-section for absorbing infrared radiation falls off exponentially with the detuning. And that's enough to get the logarithmic dependence on CO2 concentration. I won't go through all of it. This takes a few lines of equations to prove that, so I'll flash that out just to remind you. You could do it on the back of an envelope if you'd like. But that's where it comes from. So it's sort of an accident. In fact, I've looked at a lot of molecules. You look at methane. Methane is not like this. Water vapor is not like this. So as far as I know, CO2 is unique with this logarithmic dependence. Okay, well, what about line shape factors? This red curve actually has been buggered up. If you use a Voigt profile, the actual cross-section versus detuning is this blue curve. And it doesn't make much difference in the center of the line, but as you get out toward the edges of the line, you start noticing that the void profile gets a lot of absorption. So you're getting absorption at the line edges, and by the way, that's where all the warming is. It's not at the center of the bond, it's at the edges of the band. There's a lot of contribution from all of these molecules in the center frequencies. And there's so many of them, and they're so intense that they start overwhelming the few molecules that are in highly excited states and contributing most of the cross section. So the question, is this being handled correctly? And if you look again at the literature, people sort of know it might be a problem, they're trying to handle it, but it's not at all clear that it's being handled right. So let's talk a little bit about the physics behind that. All right, so here's a CO2 molecule. It's moving from right to left, and it's been excited by colliding against the nitrogen at this point, and now it's trying to radiate away its energy. The energy it radiates in the forward direction is blue shifted because, you know, the molecule is catching up with the radiation that's going in front of it. Of course, this is grotesquely exaggerated, but it gives the right idea. And the radiation behind is red shifted because it's running away from the radiation that it's emitted. And the longer wavelength here. And so this picture tells you all that's involved in line shapes in these suspect lines that we talked about earlier. So the first thing that's involved is the natural decay rate of CO2. And I mentioned that that's extremely slow. It's 1 per second. And the collision rates, such as the time between the collision that starts this out and the collision that stops it, is like a nanosecond. So it's 9 orders of magnitude difference. So as far as radiation is concerned, there's essentially negligible radiation during the lifetime of the CO2 molecule. While it does radiate a little bit, it doesn't attenuate very much, most of its energy. And there's a Doppler shift. I already mentioned Doppler shift only matters at 50 kilometers, so that's what gives you a void profile instead of a Prince profile. And finally, there's this collision transient. When you hit it, it takes a little while to excite the molecule. It takes a little while to de-excite the molecule. And that's what gives the far wings of the line. And that's the part that's very poorly understood. It's something that's almost impossible to measure. That the right way to get these numbers is to measure them. You can't measure this easily. And so the issue I'm going to close this talk with is how do you calculate the far wing line broadening that's due to this finite duration of the collision. Collision takes about a picosecond. It's sort of the time, something moving with a speed sound velocity 10 to the 4 centimeters per second, 10 to the 5 centimeters per second. It can cross a few angstroms, right? So 10 to the minus, gives you 10 to the minus 12 seconds. Okay, a picosecond. Well, the first people to really look at this, it predated quantum mechanics, and this is Joseph Larmor. Larmor did a lot of other things. He was quite interested in magnetic resonance, or at least we interpret his work as interest in magnetic resonance. He probably didn't have a clue. But among the formulas he wrote down is this very famous formula which says if you have a charge Q that's accelerating, so this is accelerating, that the power to radiate goes as the square of the acceleration, the square of the charge, 1 over the cube of the speed of light. It's one of those very simple formulas of physics. And it's really a kind of a predecessor of Fermi's golden rule. You get exactly the same formula from Fermi's golden rule in quantum mechanics. So it's amazing that he got it so early, long before quantum mechanics came on the scene. But you can write this as the mass of a particle times the characteristic time, which is incredibly short. So you call this the Larmor time often. You can read about this D&M. It's worth reading about. I strongly recommend to students here to learn a lot reading about it. But if you assume that this is how radiation works, and as I say, it agrees with Fermi's golden rule, so it's probably right, lots of people have measured this, then you find that you get a radiation reaction force that goes as the third derivative of the displacement. This is kind of surprising because you usually model oscillators that are damping with some sort of viscous damping, so the damping would go like the velocity, not the derivatives of motion. But anyway, that's what you get, and so if you then write down Newton's law, mass times acceleration is force, so here's mass times acceleration. Here's the elastic force, so this were a particle up on the spring, okay, this model of an oscillator. The radiative damping, and then whatever forces else are there. If you're having a collision, it will have force. If you have a pulse of light, it will have a force. So there's that external force. As I said, the damping is not a classical damping proportional to the velocity, proportional to the third derivative. And well, you can solve the equation of motion here to the exact solution. And, it's not numerical iteration, and I'll explain how to get it. But this black curve is the force that has hit an oscillator, say a CO2 molecule. So it's like this is a molecule here. I hit it, and you can hear it ringing, right? And so this is the period of ringing here. So there's an impulsive force, and there's a period of ringing. And this damps down pretty quickly, but I'm going to stop it by grabbing it. So there's a second force when you grab it, right? And that's how CO2 rings, right? Impulsive excitation, impulsive de-excitation. You can see both the impulsive excitation force here is an oscillating force, impulsive de-excitation force. After this completely stops the ringing. So you can work through the details. This is the internal energy of the oscillator. It's pumped up by the exciting collision, then it decays here radiatively, so this is radiative decay, and then a second collision takes out all the remaining energy and warms the gas. So you can think of this as a gas cooling collision, and this is a gas warming collision. This is the radiation difference between the radiation coming off the space. So this, it turns out it's easy to actually solve these equations, and the key is a little known function which I highly recommend, especially to students who have a jump on your competitors who can learn how to use it. This is the Dayeva function here. It's one of those functions like the Euler exponential, which is sort of protean. You can use the Euler exponential, sines and cosines or damping, God knows what you can do with it. It's amazing. And you can do the same thing with the Dayeva function. For example, if you write the Dayeva function as a function of the complex variable, a trajectory in the complex plane that's off the real axis but parallel to the real axis and above it is a Voigt profile. So Voigt profiles are the Dayeva functions. Right on the real axis, the real part of the Dayeva function is a Gaussian, perfect Gaussian. You know, if you take trajectories up and down in this, you can get the error function, you know, and Fresnel integral. So this is really sort of the key to many problems that we do in different ways in physics. But if you want a quick way to do it, the way to do it now with modern mathematics is to learn how to use this function. And you can call it in a subroutine, just like a sine or a cosine. So you get rid of enormous amounts of aggravating, tedious, confusing calculations. So, okay, today you only one for that. All right, well, if you take this model of the damping oscillator, you can also calculate the cross-section. So here's what you calculate. And it makes perfect sense. You get a cross-section here, vertical axis, that goes as the fourth power of the frequency, or frequency below resonance. In these units, resonance frequency of 1. And this is the Rayleigh scattering regime. So this is what you see if you look up at the atmosphere. You see the beautiful blue sky, because blue light is half the wavelength of red light, so it scatters 2 to 4 times more intensely, so 16 times more intensely, so the sky looks blue. And if you go above resonance, you go to the constant scattering limit, where the scattering cross-section is independent of frequency. And again, you can see that in connection with sunlight during an eclipse. The solar corona, if you look at the corona here, that's constant scattering of the free electrons in this extremely hot plasma out here. So the sun provides both examples of radio scattering and constant scattering under the right conditions. And then for CO2 and for global warming, the whole action is in this narrow spike in the center. So these edges of the CO2 line, they're so small they don't have any effect at all. Again, a question for the student. If you look at the blue radiant scattering, this is sunlight that's scattered. Put it through a spectrometer. You see indeed as though you just use a prism, but you see the dark lines of the sun. You still see the sodium lines, the iron, the calcium, or the ABC. They're all there. A little more fuzzy, slightly, not very much. But if you look at the scattering of sunlight on the solar corona, you don't see the D lines at all. You don't see any F lines. You don't see any brown upper lines. Why is that? This is a question for the students. Or I guess if they're really smart PhDs. It's historically a very important fact. Yeah. That this was when people first started doing spectroscopy on the solar corona during eclipses, you don't get any chances. It takes a long time before you get good data. But they noticed that all the brown copper lines were gone. So this was a completely smooth spectrum. But otherwise, it looked like sunlight. It didn't have this bluing that you get from radio scattering. And so this was the first evidence that the plasma temperature here was, up close to 1 million degrees. It was a Doppler shift. So the Doppler shift from the electron was so large in the solar corona, of the very lot of electrons that it smears out the brown upper line. There is Doppler shift of the Raman too, but it's very, very, very small. So you hardly notice it. Okay, so lots of interesting physics there. Okay, so here's a quick outline of how you do this calculation. You assume you have a force that has an envelope. It takes a little time for the molecule to collide and recoil. You describe it with an envelope. You take the Fourier transform with an envelope. I saw Lauren Warren said, "Do you like Fourier transform?" Yes, I love Fourier transform. So here's an example where you use them. And it turns out that the line shape factor is just a Lorentzian or a Voigt profile, and it's modulated by the square Fourier transform of the force envelope. That's all it is. So it's extremely simple. And if you let me try and finish this. So this is what the Far-Wing breeze should look like. The Voigt profile assumes that you have an impulse that's infinitely short in time. That's of course nonsense. That can't happen. And here are some possible force envelopes. You could take a double exponential, you could take a hyperbolic cosecant, or you could take a Gaussian, and all of them give far wings that fall very much faster than the Lorentzian by many orders of magnitude. This is a long tail. This is 10 orders of magnitude here. So it's a huge effect. And so the question is, have these far wing factors been properly included? And they make a big difference. So, for example, this is a region that is involved in global warming, 570 wave numbers. It's just for maximum sensitivity doubling. And what I'm showing here is the cross sections for Lorentz-Brodmann or Voigt-Brodmann lines compared to lines in which you cut them off because of the finite duration of the collision. You get much smaller cross sections, much less radiation transfer if you use realistic far wings than if you just blindly use Voigt profiles. So people need to get this right. The right way to do it is someone needs to figure out a good experimental way to do these measurements. I'd like to do that, but I haven't had time to really focus on that. So here, this will give you some feeling for why it makes a difference. I mentioned these downloading curves, but the blue downloading is taking a realistic finite duration collision, and the red curve is pure void, so you don't bother to do that. It's not enough, not a big difference, but it's enough that it makes a difference especially in the global warming, because all of the action is out at the edges of the line. The lines are the same in the specific band. And this is actually, okay, so put in the numbers. If you use the Voigt profile without any thought, you get about 40% more forcing than really should be there. It's clearly not there. It's an artifact of the wrong line shape. And so we really need to measure these things experimentally. And they have been sort of measured indirectly experimentally. This is a balloon experiment. You can read about it in a recent book by Hartman et al. A few years ago. So you've got a balloon floating here above the atmosphere, and you look at a slant through the Earth's atmosphere at the emission of the CO2 band. There's not much water left at these altitudes, so you're seeing there the pure CO2. And so the black curve is the theoretical predictions, assuming the Voigt profile. And the pink curve here is what's actually observed. So in fact, the CO2 bands in fact do radiate much less than you would expect from Voigt profiles here. Okay, prediction, pure Voigt profiles. Okay, so I'm going to close with a video clip. Someone we should all respect. I know when I was a student here, I had great respect for Feynman. His classmate, I don't know if anyone remembers Victor Maskett, but he and Feynman were high school classmates together. So here's Feynman.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Thank you.
So I know we've run over. Some of you have to run. Why don't we do that, because it might make some noise, and then I'll take questions after. One back here. Just hold for a second because it's going to be loud until people who are late hearing that.
Well, very nice presentation. I can imagine some experiments that you could do with this. For example, with cavity breakdown spectroscopy, it's possible to build a big cell. You have 1 atmospheric gas with a high concentration of CO2. Would have a path length of a kilometer. People do this all the time in molecular spectroscopy laboratories to make some experimental measurements of those line shapes. Now, I understand also that you don't have that set up in the laboratory, but the way to inspire people to actually make those measurements would be to publish these results in a place like this Review Letters. And are you in the process of writing something up that would be, and PRL is actually what I would suggest precisely because the editor, Pierre Meister, is someone who is very open to a range of ideas associated with climate. Have you put together such a paper yet?
Yeah, I'm close. You know, it's going a little slow because I have a co-author who's very stubborn, and that's Freeman Dyson, and so but we're close. You know, I think I'm beating him down. But you're right, of course you're right, yeah. Well, one of the interesting suggestions that was made by Ed Grove, if you remember, is that I work a deal with the LIGO people and use their tunnel, but I didn't have the nerve to bring it up with them. Yeah.
Well, you focused on, the last decade of measurements.
Yeah.
Climate, as you know, is a long-term issue and
Yeah.
problem. So it's really the
Right.
multi-decadal trend that's important. And
Right.
so what the observations show, tell me if you disagree with it, the IPCC says we're up by 0.85 degrees Celsius since 1875, with, I don't know the number, but about half of that since 1970 or so, as you showed. So, and, the models do a good job of representing the trend in climate over that period. So, it just seems a little disingenuous to focus on one period and not consider the other periods at additional time.
Okay, it's a good point, and you say the models have done a good job explaining the past, and we did a good job in my book, in 1982, but just as good as anybody. And what we were doing was fitting curves. And my John von Neumann at Princeton years ago said, give me 4 parameters, I'll fit an elephant, and you give me 5, I'll make his trunk wiggle. And so what we could not do, and nobody else has done, is we failed on predictions. You heard Feynman, he says, you make a prediction. If the prediction comes true, then people should take you seriously. If it doesn't come true, well, it's wrong. So now, to get people to take climate science seriously, we have to make predictions that come true, and not retrodictions, because you can always fit the past. People make money on stock market predicting the past, and if they get out of town soon enough with their loot, they're rich for the rest of their life. Because of course it always fails. It's great at retrodicting, it doesn't predict. So I think the issue is that no one has shown that they can predict anything in any serious way. I mean, maybe, I don't know, do you think they have predicted? Of course they haven't.
Well, there's a lot of uncertainties in the models, and I think that's captured within the range that you cited of 1.5 to 4.5 degrees for the climate sensitivity parameter. So.
Right. Yeah. I think that sensitivity parameter could actually be less than 1. It's just not constrained very well by observations now. And, people who look seriously at this, certainly the prime suspect is not far-wing line broadening. I think that's one thing that's interesting to look at, especially for me, it's kind of my field. But I think overall it's probably something to do with clouds, because that is so difficult to model. And I showed you the picture of the Earth, our beautiful Earth. All you see is clouds, and you don't even see the cirrus on that. And clouds can warm, they can cool. It's a really complicated issue.
Can I add something on the front?
Mm.
When you look at the Earth shine, they use the moon, the amount of light coming back from the moon to estimate the albedo.
Right.
And they found that there was an inflection point around the same time as the albedo. So there has been a change in the amount of clouds since about 19.
That's right. The cloud cover increased after that.
Right.
That's right. And so that may have been, this current slowdown would be consistent with more cloudiness, in the last 10 years. But, the experiments, they're hard to make. That was actually Steve Koonin was one of the co-authors of that paper. Yeah. That's a very interesting paper.
Are there other questions? Yes.
I mean, the data doesn't show any temperature change, but I wonder what we can make about all this stuff about the Arctic melting and glaciers receding and new species appearing.
Mm.
I mean, is there something
Well,
going on, or is it all captured by the constant?
Well, ice is actually increasing around Antarctica. Every year it's more.
They claim the Arctic is melting.
Well, okay.
And they claim
If you look, any theory of global warming shows greater warming of the poles, both the Arctic and the Antarctic. It doesn't show warming of the Arctic and cooling of Antarctic. That's not, there's no way to get that from a sensible theory. And the other point is that it's true there's been warming, but the warming started roughly 1800, long before there was any increase in CO2 in the atmosphere. John Muir made a special trip to Alaska in 1879 to investigate why all the ice had disappeared from Glacier Bay. 1879. It was all gone in 1879. There practically none that melted after that. Tiny fraction melted after that. And so there has been warming, but it started long before CO2 started increasing.
If you look at the Antarctic melting, and you look at the latitude and then compare it with Greenland, you'll find that it's moderately south of Greenland, so it's not really at a latitude you might expect melting, because it's that little finger that's heading towards South America that's melting, but not on
the peninsula,
but not on the east side.
But if you look at sea ice, for example, every year it reaches a new record in Antarctica.
I'm going to take one question back here.
Well, your talk is concentrated on CO2, but you mentioned that water vapor is also extremely important. We understand water vapor in all of these models.
No,
is that a bigger uncertainty than what we've been dealing with today?
There's a big mystery there of what they call continuum absorption of water. And I think it's still very debatable what that is. It may be connected with this far-wing broadening, but other theories are it might be polymers of water, dimers, trimers of water. So I think it could be anything right now, and it's very open research subject. But water is, you're right, it's more potent than CO2, and it's much more complicated, so at least CO2 doesn't condense. It's 400 parts per million in the stratosphere, just like it is in the troposphere, but there's practically no water once you get, high enough, but it freezes out. A little bit, not much.
And most of the interesting physical stuff that you're showing is above 30 kilometers, where there aren't very many molecules left. And so, but down closer to Europe, everything's kind of smooth when you fly anything versus, the gross totals. They're quite smooth. So, isn't it better to have kind of a plumber working with you who looks at the averages rather than just the nice little fancy stuff, And most of the stuff, at 20 kilometers, you're gone through 75% of the atmosphere.
Yeah, that's right.
So, you just concentrate below 20 kilometers, it seems to me your average is...
Well, I think in defense of below 20 kilometers, that's where we live, So the effects of CO2, we're interested in their effects at the surface, close to the surface.
All right, I'm going to exercise chair prerogative and ask a question. This is about the actual physics. So we would call what you're measuring the curve of growth is the sensitivity, right?
That's correct.
And so it's clear that the wings can be stronger or weaker depending on how you calculate that.
Right.
But would that actually change the slope? In other words, the amount of change?
As I mentioned,
changes both the offset and the slope.
Yes, it changes the slope by about 40%.
Okay, so that was from the slope.
That was what I meant by that. But thank you for clarifying. Yeah.
All right, since we're over time, our speaker has to be with students in about 10 minutes, so we're going to let you have a short break. Then we're going to have a meeting with the graduate students.
Great. Okay.
Thank you all for coming.
You mentioned that CO2 is unique with that logarithmic. With other gases, methane, if it was at 400 parts per million, would it have a logarithmic?
It doesn't
like
look.
that?
I have looked a little bit at that. It doesn't look like it. Methane has a more complicated vibrational structure, and it doesn't have these same funny Fermi resonances. But of course, methane's levels are much lower.